Well, good evening. Tonight we're going to be talking about some advanced data modeling techniques, including inheritance and composite keys. But first, we're going to be going over, we're going to have you do Lab 2. It is a graded event. The instructions are in our Sky course site, in the resources folder, in the hands-on exercises, hands-on 2 subfolders. So go ahead, and you have the option of working in a group, or if you can form one, or doing it individually. It should be no problem either way. So take time to do that, and then we'll continue with the lecture. Okay, so in this chapter, we're going to learn about the extended entity relationship model capabilities, clusters, supertypes, subtypes, and composite keys. So extended entity relationship modeling is a result of adding some semantic constructs to the original ER model that represent some of the things going on in databases today. One thing that is important is the idea of supertypes and subtypes. So consider student and instructor in our university database. They both have name, ID, and department. Student then has total credits, and instructor has salary. But we repeat name, ID, and department for each of those tables. What if we had a supertype person and put the common attributes in it, and then we had 2 subtypes with the unique attributes in each of those? That's the idea behind supertypes and subtypes. So we can also have specialization hierarchies. A student is a person and an instructor is a person, if we have this supertype set up, for example. So this hierarchy shows or provides an ability to support attribute inheritance and define supertype attributes, and we can then have disjoint or overlapping constraints. But let's take a look at how we would do something like this in Microsoft SQL Server. I'll change the share here. So in Microsoft SQL Server, the way we would do this is we would create a base table, for example, people, and we derive subtables from the base table. So we have we create our people table, then we derive the table student, person ID references people person ID. Create table, let's say instructors, and then the key person ID references the people person ID key, and so on. And then we could create a join where we join together, say, for example, a person and student. So we get all the information together. And we can also create a person type. And then we have the various types: student, teacher, or parent in this case. And then we create a table of people based on the person type, and then we can derive from that. So the idea is that this concept of inheritance is in current database offerings. We're looking at how it would be done in Microsoft SQL Server. Okay, now we'll go back to the lecture. And here we see an example of a specialization hierarchy. Employee, and then there's different types of employee. In an airline, for example, we might have pilot, mechanic, or accountant. Let me ask you, what is an entity supertype and why is it used? Well, an entity supertype is a generic entity type that we relate to one or more entity subtypes where the entity supertype contains the common characteristics or attributes, and the entity subtypes contain the unique characteristics of that particular subtype. The reason for using supertypes is to minimize the number of nulls and minimize the likelihood of redundant relationships. So then the next question is, what are subtypes? And the answer there is a subtype is a more specific entity type that's related to a supertype. And again, the supertype contains the common characteristics, and the subtypes contain each entity subtype. And now we're looking at a specialization hierarchy. What exactly is that? Think for a moment about what a specialization hierarchy is. Well, a specialization hierarchy depicts the arrangement of higher level entity supertypes, parent entities, and lower level entity subtypes, child entries. To answer the question precisely, we see this image here, and we see a hierarchy formed by an employee supertype and 3 entity subtypes: pilot, mechanic, and accountant. So in this case, we have a one-to-one relationship between an employee supertype and its subtypes. For example, a pilot subtype occurrence is related to one instance of an employee supertype, and likewise a mechanic subtype is related to one instance of a employee supertype. So inheritance enables a subtype to inherit attributes and relationships of the supertype. So for example, a student inherits the name, ID, and department from the person supertype, and then also that a student is a member of the department relationship. So those can be inherited from the person supertype. So we have this idea of a subtype discriminator, which is an attribute in the supertype that determines to which entity subtype the supertype occurrence is related. So if we know the subtype in the person, we know if we have either a student or an instructor. We can have disjoint subtypes or overlapping subtypes. So disjoint is where we have a unique subset of the supertype entity set. implementation is going to be based on the value of the subtype attribute in the supertype. With overlapping, we have non-unique subsets. Then we have the requirement for the use of one discriminator for each subtype. So here we have an example of overlapping subtypes. So we have a person, and that person can be both an employee or a student, because employees have tuition remission. They may take classes that they're interested in, and the employee can be an administrator or a professor, and a professor can actually be an administrator, for example, the dean of a college. Now here on the student side, in other words, a person can be either a student, a student or an employee. But on the employee side, we had an overlapping. The employee can be an administrator or a professor or both. With a student, you have one type, at least in this diagram. You're a graduate student or you are an undergrad, but not both types. So what is a subtype discriminator? Well, a subtype discriminator is an attribute in the supertype entity that's used to determine to which subtype the supertype occurrence is related. So for any given supertype occurrence, the value of the subtype discriminator will determine which type of supertype occurrence that subtype is related to. For example, the employee supertype may include the employee type P to indicate a professor. Overlapping subtypes are subtypes that contain unique subsets for the supertype entity set. That is, each entity instance of the supertype may appear in more than one subtype. So again, let's go back and look here. In a university environment, a person may be either an employee or a student or both, as we see here. If an employee turns out to be a professor, they may also be an administrator at the same time. Student and employee are overlapping subtypes of the type person, just as professor and administrator are overlapping subtypes of the supertype employee. Okay, let's go on. So we have this idea of a completeness. How does each supertype have to have a subtype? And a partial completeness means not every supertype occurrence is a member of a subtype. Total completeness means that every supertype occurrence must be a member of one of the subtypes. So again, a partial completeness means that not every supertype occurrence is a member of a subtype. That is, there may be some supertype occurrences that don't belong to any of the supertypes. Total completeness means that every supertype occurrence must be a member of at least one subtype. So there's two ways of setting up these type of inheritance relationships. We can start with just thinking about major entities and start at the top and do a top-down process. So we start with the idea, well, we have people in our university, so we set up a person table. But then we realize that it might make sense to put some of these into a one subtype and others into a different subtype, and just keep the common information in this person attribute. So we go from person, we still keep that, but then we add in two subtypes, student and employee. We could also go about it the other way around, where we start with a bottom-up process. So we notice that we have student and employee, like we do in our university database, and we think to ourselves, wow, there's some redundancy between the attributes in student and instructor. Why don't we create a super type and make them both subtypes? So two different approaches. An entity cluster is a virtual entity type, and it's used to represent multiple entities in an entity relationship diagram. So let's take a look at what that is. So here we see it's formed by combining multiple interrelated entities into a single abstract entity. It's considered virtual or abstract in the sense that it's not actually an entity in the final entity relationship diagram, but it's a temporary entity used to represent multiple entities and relationships with the purpose of simplifying the ERD. So in blue, we can see we have offerings and location for those offerings, but we want to combine both of those together to create an entity cluster just for convenience. So again, just to sum up, we have this idea of inheritance in databases where we can look at two entities, for example, student and instructor, notice a lot of common attributes and very few unique attributes. We think, let's create a supertype entity called person and relate the unique characteristics of student and the unique characteristics of instructor to that common supertype. And we took a look at how that's done in Microsoft SQL Server. Let's now consider the idea of primary keys. And of course, we know that a primary key is a combination of attributes that uniquely identifies a row in a table. We need to be able to do that. Now, we also have natural keys. And that is a real world identifier used to uniquely identify real world events. And it can be used as the primary key of the entity being modeled. So here's some of the desirable characteristics of creating a primary key. The primary key obviously should uniquely identify each entity instance. A primary key must be able to guarantee unique values. It cannot contain nulls. It must also be non-intelligent. And that means it should not have any embedded semantic meaning. An attribute with embedded semantic meaning is probably better used for a descriptive characteristic of an entity than as an identifier. So, for example, a student ID, let's say like 650937, would be preferred over Martha L. Smith as a primary key identifier. Another characteristic that's desirable is it doesn't change over time. If an attribute has semantic meaning, it may be subject to updates. This is why names do not make good primary keys. If you have Vicky Smith as the primary key and she happens to get married, then that might change. Primary key is subject to change, and foreign key values must be updated, thus adding to the database workload. It's preferable to have a single attribute as your primary key. Primary key should have a minimum number of attributes possible. Single key attributes are desirable, but they're not required. They simplify implementation of foreign keys. It's preferably numeric. Unique keys can be better managed when they're numeric because the database can use internal routines to implement a counter style attribute that automatically increments. And they have these auto increment capabilities when you create your own key that you add to a table. And obviously, you don't want to violate security concerns like identity theft protection mechanisms and use fields like Social Security. So we also will be using composite keys in many situations. And the use of a composite key is, well, first, a composite key is a primary key that has more than one attribute. And if you'll remember, when we put a many-to-many relationship into a relational database, we put in a composite entity that allows us to split the many-to-many into two different one-to-many relationships. And the way what we put into that composite table is the primary key from each of the tables in the many-to-many relationship. Additionally, we have this idea of a weak entity, and they have a strong identifying relationship with the primary entity. So they take the primary key from the primary entity, and it becomes part of their composite primary key. We add what's known as the discriminator to the that's in the weak entity set to the primary key from the strong entity set, and we come up with this idea of a composite key. So composite primary keys are particularly useful in two cases: as identifiers of composite entities where each primary key combination is allowed only once in a many-to-many relationship. And also as members or identifiers of weak entities where, again, that weak entity has a strong identifying relationship with the parent entity. So to illustrate the first case, assume we have a student entity and a class entity, and they're in a many-to-many relationship. So in other words, one student can take many classes and one class can have many students. We then put an enroll entity set between them. So each student enrolls, has many enrollments, and each class has many enrollments. And enroll is going to have the primary key of the student. Each record will have the primary key of the student involved in the enrollment and the primary key of the class involved in the enrollment. And together those two become the composite primary key of enrollment. And we can see an example of this here. And again, the composite primary key provides the benefit of ensuring that there cannot be duplicate values. And we are going to look at a weak entity set also. But this is an example of a many-to-many relationship. So surrogate keys are something that the database system can provide for you, and especially if it's numeric, it can provide it with an auto increment capability. So you can require that you put a auto increment in your particular table. So again, a surrogate primary key is an artificial primary key created by the database that's used to uniquely identify each occurrence when there is no good natural key available, or when the natural primary key might include multiple attributes. A surrogate primary key is also used if the natural key might be too long. You start adding a couple of attributes together, it can become quite long. So the reason for using a surrogate key is to ensure entity integrity. In other words, we always are going to be able to get to a record uniquely. And here's some example of the data used to keep track of events, start time, the date, the start time, end time, the room, event name, and size. Another thing we have to consider in database design is implementing one-to-one relationships. And typically, if again, a one-to-one relationship is implemented just as you would with a one-to-many, where you put one of the primary keys of one of the tables in the one-to-one relationship in the other table. And one of the old rules of thumb is, well, which table donates the primary key to the other? And you would do an analysis of which one would create the fewest nulls. So for example, we might consider something like the dean of a department. It might make sense to put the professor ID or employee number in the department table because each department record will have an employee that's the dean. And so that's probably a better way of putting it in. We could have a field like dean in employee, but that would have a lot of nulls. And so probably best to implement it like this. Another thing we might want to consider is maintaining a history of time variant data. So that's going to be data that changes over time. So for example, we were just talking about deans. Over time, the dean of each college will change. So what we might want to do if we want to have a history of all the deans in a particular college is create another table and have a one-to-one relationship with the original entity. I'm sorry, a one-to-many relationship, so that, you know, each department will have had many deans in its history. And another example of maintaining history might be each employee is going to have a salary, but over time that salary changes. So we might want to keep a record for each salary that an employee has. So we create an employee salary history table, and we establish a one-to-many relationship. And from that, we can find out the history of an employee's salary over time. Manager history, same thing. Who's been a manager for a particular department or for a particular employee. So, what are time variant data, and how would you deal with such data from a database design point of view? Well, as the label implies, time variant data are time sensitive. So if you want, for example, as an example, a university wants to keep track of the history of all administrative appointments by the date of appointment, date of termination, and so on, you would do something like this. Put in a table and keep a history in that table. Okay, we also, in our design, want to avoid certain problems. And one of those is fan traps. And a fan trap is something that happens when you have two one-to-many relationships coming out of one entity. So this is the opposite of what we do when we have a composite entity where we have two one-to-many relationships going into that composite entity. Here we have an error. We have two different one-to-many relationships coming out of a particular entity. In this case, it's dealing with sports teams that are organized into divisions, teams, and then, of course, each team has players. Well, the way it's organized now, you go to the division and you can find teams or you can find players, but you're not going to be able to find the players on a particular team. So this is an incorrect design. So a way to correct it is to have one-to-many relationship between division to team. And so then you can go and you can find, okay, for U18, we have Blue Stars and the Panthers. And then go from team to player. And for the Panthers, we have these players. And then we also have a possibility of redundant relationships. And so here we have, of course, the relationship we just described. And we can also go from division to player. So we have to be consistent across the model in our database design. So what is the most common design trap? It's a fan trap, and that occurs when you have one entity and two one-to-many relationships coming out of it. And again, that causes some problems. Okay, any questions? All right. Thank you.